Okay, let's go ahead and get started. Um, our good friend and brother Clark is not here with us today. Clark and I went to a conference in Rexburg over the weekend, and on Saturday morning he was feeling very weak and dizzy, and then as the day went on he lost feeling in his right arm and then strength in his right arm. So his wife took him to the doctor on Monday, and what they found with an MRI was a tumor in his brain the size of a racquetball. And so he's scheduled for surgery on next Friday, a week from tomorrow. So I will be teaching the lectures, and Clark was just passionate about nuclear radiation and the effects that had on the human body. That's not my passion, so that's not where we're going to go. There will be coverage on the exam covering that nuclear decay lecture that he gave, but that would be the only nuclear component there. I will be fasting for Clark next Friday, and I would invite you to remember him in your prayers. His spirits are good. He is very positive. His wife is trying to be positive, but every now and again I see tears. So that has to be hard. Would someone be willing to give us an opening prayer?
Dear Heavenly Father, we are thankful today for the life that each of us has. We are very thankful for Professor Francis and Clark, all that they have done for each of us at this time. Father, we're thankful so much for the technology that we have today to both learn and to help each of us in our lives. Pray at this time for a blessing on Mark as he prepares for surgery, that his body and his mind will be strengthened, that the doctors will be able to perform the surgery well, and that he'll be able to make a full recovery. We pray at this time that we may be able to learn more and to always show gratitude for what we have this day. And we pray that we'll continue to better understand polarization as taught by Professor Francis. And we love you, Father, and keep this in our hearts and minds this day. We say this in the name of Jesus Christ. Amen.
Amen. Thank you. What we will be covering next week on Tuesday is special relativity. I just think, you've taken 2 semesters of physics, you ought to know something about Einstein's theory of relativity. And then on Thursday, because there are often questions about the photoelectric effect and half-life, those sorts of questions, I will cover that on the last lecture. Well, actually, the last lecture would be the following Tuesday, where we're just going to review for the last exam. And as I've told you before, the last exam is not cumulative. It's just on the new material since the 3rd midterm. So that's where we're headed. This homework that's due Friday, number 21, there were a number of errors in the key, and I take responsibility for that. I had hired a very gifted student to take my questions and put them into max. And I had been checking every week that everything was good to go. But she was so good and so consistent that this week with everything going on, I just assumed that it would be fine, and there were places where it wasn't. In every case, I fixed the key, and I've told Max to regrade, but only change the score if it would make your score go up. So what that means is that some of you have correct, you have all the points, but for incorrect answers. And I warn you that you really need to go and look at the key, look at my solutions, and make sure that you're getting the points for the right reasoning. Now, it also means that if you're just going to a friend and saying, what's the answer that gets the right points? If you get their wrong answer, it's not giving you the full points anymore. We fixed them. So you want to make sure that what you put in is right, regardless of what you hear from others. Questions on that? Yes.
Is this for the homework that was due last Friday or this Friday?
21, which is due this Friday. Yeah. Okay, let's get started. I find that a lot of us are still struggling between curvature and radius of curvature. And some of us are wondering, where do I put that radius of curvature? Well, when you have positive curvature, you're moving forward to a point, okay? And so that means the center of the circle that represents that curvature is in front of you. I don't want you to remember right or left. Because you could have the beam going to the right or left. It's just in front of you in the direction that the wave is traveling. On the other hand, if the wavefront is negative and the wave is diverging, spreading out, okay, now the circle that represents that wavefront has its center behind, back where you've been, okay? And so when you're finding those locations, you have to ask yourself, is this positive curvature, so I go in front, or is this negative curvature where I go back behind? Does that make sense? Questions on that? Okay, I find that some of us are still struggling with more than one lens, that still is causing grief. And so last time we worked a problem where there was a negative lens and a positive mirror. This one, I've got a positive lens and a negative mirror. Okay, and we'll just go through this really quick. The power of the lens is a +5. The power of the mirror is a -2.5. These are numbers that you've seen before. What's the focal length for a +5 lens? Tell your neighbor real quick. What's the focal length of a +5 lens? Okay. I hope you all just quickly said 20 centimeters. How did you get that? Greg, how did you get that? Well, remember, power is equal to 1 over the focal length of the converging lens. And so that means the focal length is going to be 1 over the power. That's going to be 1 over 5. A diopter is just a inverse meter. That's going to be 0.2 meters, 20 centimeters. Okay, I hope you're bored. That's where you're supposed to be. In the same vein, the -2.5 is going to have a that's going to have a focal length of 40 centimeters. Now, let's first of all look at what happens to that. Let's just look at the light that leaves the tip of this arrow, okay? And ask ourselves, what curvature does it have when it gets to this first lens? Well, I've written it in red. It's negative because the light from that tip is spreading out. And because it's 40 centimeters away, or 0.4 meters, 1 over 0.4 is 2.5. And so the curvature, right when it gets right here, is going to be negative 2.5. And then the lens does its thing. It messes with it. And that ends up giving the curvature on this side of the lens is now positive. And so that means it's heading this direction. It's curved with a center over here. And that center over here would be 40 centimeters away. And that would be where all the light that left the tip there would come back together there. All come back together and pass right through, spreading out again, okay? Then that wave, now right here, the curvature goes to positive infinity, and then it becomes negative. The wave starts spreading out again. And so my curvature, when I get here, this is 20 centimeters. And so that's going to be a curvature of -5. And the power of this mirror is -2.5. And that gives me a total curvature of -0.7 or 7.5. And now things are turned around, moving to the left, going the other way. Now, really quick, find out where that second image is. Where's the second image? See if you can get the location before your neighbor can. Yeah, it's coming in with positive curvature down to a point. And if I look at the rays, okay. So if you plug 7.5 into your calculator and hit that 1 over button, which is your friend, that's going to be your very best friend during the exam. What you get is a number that is 0.133. So it would be behind, okay, because now it's negative curvature, it's moving to the left. That means it's curving like this, which means that the center of curvature would be behind, and it would be 13.3 centimeters behind. Okay. Now that curvature of -7.5 is right there. And then it evolves as it heads to the left. And by the time it gets here, what kind of number would you expect? The magnitude, the size, would it be a bigger number than 7.5 or a smaller number than 7.5? Shout it out. Yeah, a mighty shout went up throughout the land. It'd be smaller because as it spreads out, it has a bigger radius. It's less curved. Okay, the curvature goes down as it evolves there for a negative expanding wave. So I would expect that to be something smaller. And indeed, I would find that by saying, Well, it started here. And it went 13.3 centimeters and 60, that's 73.3 centimeters. That is 0.733 meters is equal to the R. And so that means the curvature is going to be 1 over 0.733, and it's negative. And so if I do that, what I get is negative 1.36. Okay, so it's a smaller magnitude because it's less curved. Okay, and then I add the 5 diopter of the lens, and I get a positive number, positive 3.64. If you plug in let's see, the radius is equal to 1 over the curvature. If I go 1 over 3.64, what I get is 27.5 centimeters, 0.275 meters. Okay, and because this is positive curvature and it's moving to the left, this was, when it comes out of that lens, it's going to be positive curvature. And so the radius is going to be in front of it in the direction it's going. Questions on that? Yes, sir.
How do you know whether the image will be up or down?
I'm sorry?
How do you know whether the image will be up or down?
Oh, well, let's talk about that. Thank you. I did not pay that gentleman. I did not give him any money. Okay, but I wish I had. Okay, first of all, let's look at this first image. It's the image of a converging lens where I've got the object further away than the focal point. The focal point's here and it's further away. So am I going to get a real image or a virtual image from that one?
Real.
Yeah, I can look right here and that's a real image. And so, well, let's answer this question first. What about this last image?
Real.
Is that going to be real or imaginary or virtual?
Real.
It's got to be real because I've got a positive final curvature, okay? But let's look at image to image. I said this one was upside down because it's real. And if I just consider this one lens all by its onesies, what I get is something that's flipped upside down. Why did I make it the same size? Yeah, because it's the object and the image are the same distance from the lens. I cooked the numbers to make it easy, okay? And now I put this in front of that mirror, and I know that this is the simple kind of mirror, the kind that you've got on the sides of your car that doesn't flip the trucks upside down as you're driving, right? That's a feature, not a bug, okay? And so that means the image over here is going to be, it's going to be on the same side as the object. This is the thing creating that image, and so they have to be oriented the same. And the reason I put 2 centimeters there is that if you take the this is 20 centimeters, that's 13.3. If I take the ratio of 13.3 over 20, I get 2/3. Okay, and so the height is going to be 2/3. And since it started with 3 centimeters, 2 centimeters. Okay. Now, this image is going to form, since this is way further than the focal length, this is going to form a real image that's going to be inverted from that. And its height is going to be 0.75 centimeters. And I got that by just taking the ratio of the distances from this final lens. 27.5 divided by 73.3 that gives me the ratio. And when I multiply that by the 2 centimeters, I got 0.75. Yes, Miriam.
Is that ratio the same as the magnification equation?
Yes, exactly the same. That is exactly the same. All I'm doing is taking DI over DO. There's a minus sign in that equation that we don't need because we just keep using curvature. Good, sir.
Does magnification affect if it's a rect or flipped?
The magnification equation has that minus sign in there so that whenever you get a negative number, it's inverted. Whenever you get a positive number, it's not inverted. However, that requires that you know all of the rules in those great big tables of when to make your DI positive and when to make it negative. So I would not count on that. I would just take it a lens at a time and say, you know, is this one gonna flip it? Is this one gonna flip it? There's another way of doing it, and it's one that always works. You remember last day, we had a question of why this one was upright when this one was down. Okay, why was that upright? And so the way of really showing whether it's on top or on the bottom is with a ray diagram. And that's the point of this week's tutorial. That's why I gave this handout last day, is so that you could do careful ray diagrams to find out where the image is and how it's oriented. And you'll never turn this in, but this is so you can use a ruler and do careful work instead of just sloppily putting lines on a computer screen, okay? And if you didn't get one of these, pick one up on your way out the door. So let's do the ray diagram now. You remember the 2 rays that we always use. We know that with a power of +10, the focal point, the focal length is going to be 10 centimeters. So that's going to be the near focal point. That's going to be the far focal point. Okay. Now, the first ray goes through that focal point and comes off parallel to the principal axis. And if this lens did not exist, if it were not there, this would just keep on going. Okay. So I'm looking for this image first. The second ray goes parallel to the principal axis, and then it goes through that far focal point. And again, if this lens did not exist, it'd just keep on going. Okay. Now there's a third lens, a third ray that would go right through the center here. Okay. But I'm going to look at another ray, a ray that's not one of the principal rays, a ray that you gotta just be a wily old man to see it. I can extend the plane of the lens, and you know, I just drew a size for the lens. It could have been bigger. Okay. There's going to be one ray that's going to be bent in just the right way so that it goes through the center of this second lens. And I know that if it goes through the center, the symmetry of that second lens, it's not going to be bent. It's going to go straight through. Okay. And I know that it also has to end up there because all of the light that ends up, that started here would have ended up there had there not been a lens. And this ray is not affected by the lens. Well, now let's look at the green one. The green one didn't goes straight when it went through this lens. We know that a ray that comes in parallel to the axis, if it goes into a negative lens, is going to be spread. And it's this one that's parallel to the principal axis is going to be spread in such a way that it looks like it's coming from this near focal point right here. And if I look at these two rays here, they cross right there. And that tells me that that had to be on the upside. Okay. And it also tells me how big it is, because this is twice as far away from this lens as this is. That was just a question that was asked last day, and I didn't want it to go unanswered. Okay. Hannah, you look troubled. So it's okay?
Yeah, going backwards, like from the ray that's coming in parallel and then converging down, tracing the line backwards, I'm still wrong.
Well, you remember that that's the big difference between positive lenses and negative lenses. A positive lens that's fatter in the middle will take all the parallel rays and bring them down to the far focal point. But a diverging lens takes all of those and spreads them as if they were coming from the near focal point back here. That's how we figure out how much they get spread. Okay. Okay. Let's talk about something different. When you're looking at the heavens and trying to figure out how far apart things are, what we're really trying to figure out is how far are they in angle? How much are they separated in angle? Okay, because without using parallax, we really can't tell, how far they are away. We can just see how far they are spread. Okay, now we call that the angular separation. And last day we talked about the fact that the angular separation from one side of the moon to the other is about the same as the angular separation from one side of the sun to the other. Correct? Now, a telescope just magnifies that angular separation of objects. And the way it does it, you're pretty much constrained, since things are so far away, that you're going to be dealing with rays that are coming in parallel to each other. And we know that those rays that come in parallel to each other are going to be focused on what we call the focal plane of the lens. The focal length, you set up a plane that's perpendicular to the symmetry axis, and this light is going to end up somewhere on that plane. Now, for a telescope, you just have a second lens, the eyepiece, and you use that eyepiece to focus on that real image that's formed right here at the focal point, focal plane rather, of the objective lens. Now, we find that the length of that telescope is just going to be the combined lengths of the focal lengths. You take the focal length of the objective and the focal length of the eyepiece, you add those together, that's going to be the length of your telescope. Okay. However, you want this focal length to be as big as possible so that you create as big a real image as possible. All the better to see it with, my dear. Okay. Now, that means that objective lens really should have, if it's got a long focal length, Is it fat or is it flat? Fat or flat? Yeah. Remember, the fatter the lens is, the smaller the focal length. And so we want that objective lens to be almost flat. I mean, you look at it, you say, oh man, that's just a piece of glass. We could put that in my front room. Okay. But when they're creating the telescope, they go to great lengths to make the curvature just right, enough to have a really, really long focal length. On the other hand, this one here, you want that one to have as small a focal length as possible. You want that one to be a super duper magnifier. Okay, remember we talked about magnifying glasses last day. And it turns out that the angular separation that you're going to see is going to be now determined by that angle beta. This is what you would have seen with the naked eye. And so if I take this angle beta and divide it by that angle alpha, that's going to give me the angular magnification of the telescope. This is what I would have gotten without the telescope. This is what I get with the telescope. How much better is this than that? And so that turns out to be your magnification. Now, with a little trigonometry, a little right angle trigonometry, you can show that that's also with these triangles here, that's equal to the focal length of the objective lens divided by the focal length of the eyepiece. So you see, if you make that as big as possible and that as small as possible, you get the most magnification. See if your neighbor is following what I'm saying, if they're picking up what I'm putting down. Okay. I am not an astronomer, okay? I taught at Montana State University for 31 years. The biggest physics class at Montana State University is Mysteries of the Skies 101. It's just a general astronomy class. And I went out of my way to make sure that I never, ever taught that class. Why? Because that was the class that all the football players took. And I did not want to deal with that. Okay, so I've gone out of my way to learn as little about astronomy as possible, I'm ashamed to say. But so I wouldn't expect a whole lot of questions about telescopes on the last exam is what I'm saying, okay? Now, a microscope works on a very, very different principle. And that is that with the telescope, there's nothing I can do about the location of the thing I'm looking at. But when I'm using a microscope to try to get a bigger angular separation, I've got all sorts of liberty of where I want to put that sample, where I want to put that slide, okay? And so you remember that if I use an objective lens to make a real image, and then I use my eyepiece to look at that real image, well, if I set up these distances just right so that my real image is just inside the focal length of the eyepiece lens, you remember what happens there. If it's just really close to that focal point, the image is going to be a virtual image because it's closer than the focal point, and it's going to be huge. It's going to be almost out at infinity. And so now you can look at it and get a good view. Okay, so that's what we do with a compound mic. And when I say we, I mean you biologists and pre-med students. Bless you, okay? So. Now, the magnification there is just the magnification of the eyepiece times the magnification of the objective lens. And we treat that eyepiece just as if it were a magnifying glass. And you remember last day that if we had a magnifying glass and we had a relaxed eye where we were just kind of looking out towards infinity, the magnification was in the near point over the focal length. And then for the objective lens, whoops, wrong direction. The objective lens, I want this length here. And so that's going to be L minus the focal length of the eyepiece. And for most telescopes, you want a really, really small focal length for your eyepiece. And so this is pretty much just going to be L. So you see that for the magnification of a microscope, you want both of your lenses to be really, really fat, okay? You want these focal lengths to be very small. That'll give you the biggest magnification, okay? Okay, now, where we're going now requires us to remember some things from Physics 105. Oh, Greg, I don't want to. It was so long ago. It's okay. It's not going to hurt. Not going to hurt. You remember that we represent these light rays with a line, with an arrow. But we remember every now and again that it's really a wave. And we can think of these crests as wave fronts. And indeed, that's what we're drawing up here, is wave fronts, okay? Those are the crests. But instead of going straight, it's spreading out, okay? And that's why these are curved. And it's that curvature that we've been using to find our answers. Now, we talked in 105 about interference when we had more than one wave. And we found that if we had two waves that were in phase with each other, okay? In phase means where I've got a crest in the blue, I've got a crest in the red. Where I've got a trough in the blue, I've got a trough in the red. Those add together to give me a super crest and a super trough, a super crest, a super trough. We've been here before. On the other hand, and these would be the crests for the blue, these would be the crests for the red, and that just add, that'd be higher, okay? Now, for destructive interference, and that's where we're headed, if the blue is out of phase with the red, okay? And in this case, it's exactly 1/2 wavelength out of phase. In other words, I've taken the blue wave, I've colored it red, and I've moved it 1/2 wavelength to the right. You see that? So it's 1/2 wavelength out of phase. And now you see where I've got a crest of the red, I've got a trough of the blue. A crest of the blue, I got a trough of the red. And so what I get is flat, nothing. It cancels out. Okay. Now, if that's the crest of the blue and that's the crest of the red, when I add them together, what I get is nothing. Now, I have a demonstration of that with sound, not with light, but I've got these two out of phase, where one's sending out a crest, the other one's sending out a trough. If I put them in phase, you hear it louder, right? Okay, now let me put it out of phase again. And if I point them towards each other. Do you hear anything in the back? I'm having a hard time hearing it, but there I can hear it. Now, if I change the path length, that's gonna make it so that some of you are hearing something louder and some of you are hearing something softer. For how many of you did it go softer? Raise your hand. Over there, okay, you're in a dead spot where you've got cancellation. Is anyone now in a dead spot that wasn't before? Back there, okay. Okay, if I up the frequency, we're gonna get more dead spots. Who's in a dead spot now? Okay. Okay. That's just irritating. Okay. So it's this destructive interference that we're going to be talking about for the next few minutes here. If I have, this is what we call a diffraction grating, where we've got little grooves in some sort of reflective material, something that will bounce light off of it. And so you see that when I have a distance d between this surface and the bottom of the little groove, any light that comes in and bounces in the groove is going to travel further than any light that bounces off this part here. And the difference in path length is going to be twice that distance, the depth of the groove. Everyone see that? Okay. Now, when those two waves, this one that went into the groove and this one that didn't, when they meet up out here, are they going to be in phase or out of phase? Well, it depends on this distance 2d, the extra path that this one had to travel. If that's equal to a integer number of wavelengths, then it's just going to be back in phase again. You know, sure, there were 3 extra wavelengths in here, but when it came out, it was still going crest when the other one was going crest. Okay. Now, if on the other hand, I've got an integer number plus 1/2, that throws in an extra half wavelength, and now I would have destructive interference. See if your neighbor understood what I just said. Do a buddy check.
Well, so. With the destructive is under that 1/2 wavelength. But because it's like it was just like.
Okay.
It's like going in and out. It's not changing.
So
If you did plus.
you see that these conditions depend on the wavelength of the light. And so that means that for this distance d, some wavelengths are going to be reflected brightly, and some wavelengths are not going to be reflected at all. They're going to cancel out. Okay. And that's all there is. That's all there is. Now, instead of a diffraction grating, we're going to put a film on some reflective surface. This could be, you know, a coating on an optic lens. It could be oil on water. It's just some thin film. And it has thickness T, which means that this wave has to go an extra distance of 2T. There's a T and there's a T that it has to go, okay? And again, if that distance that it has to go is an integer number of the wavelength, but it's not the wavelength in air, now we've got something going, it's traveling in some medium where it slows down. So if this is water, that's going to be the wavelength divided by 1.33. Okay, it slows down the wave. But otherwise, I've got exactly the same formulas that I had before with the diffraction grating. Simple, 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 simple. Oh.
If it only were that simple.
Have you seen that sketch? I love it. Okay. If only it were that simple. If only it were that simple.
The change stands for.
The change in S is the difference in path length. This ray just had to go from here to here. The other ray had to go from all the way to there and there. And so this one had to go an extra distance, T and T. Okay, the delta S is the extra path length. The difference in path length. Okay. Now, you remember from 105, I hope, that when we had a pulse, any kind of energy that was going from one medium to another medium, we ended up with some of the energy bouncing back, being reflected. And it mattered whether we were going into a free end or whether we were going into a fixed end. You remember if we had a free end, what happened was if the pulse came in on top, it went out on top. It didn't get flipped. On the other hand, it's upright. On the other hand, if we send that pulse into a fixed end where it's tied to the wall, now it tries to lift the wall, but it can't. And so instead, the wall inverts the pulse and it comes out on the bottom. It gets inverted. Okay. Do we remember that from 105? Good. Okay. Now, remember I had two wave machines, one that was fast and one that was slow. And I can think of the slow wave machine as, if we're dealing with light, as a medium that had a big end. You remember, the bigger the end, the slower the light moves in that medium. And this would be a medium where I have a fast wave, a small end, like air, okay? And what we find is if we go from the slow to the fast, or the big end to the little end, what happens is it bounces back with no flippage, okay? And so what I have is crest in, crest out, and I never get any flippage for the transmitted energy. Never do, okay? Crest in, crest out. And this is what it looks like. Okay, it comes in on the slow, and then it just bounces back on the same side. Is that all coming back? Okay. On the other hand, if I come in from the fast side and hit the slow side, that's like hitting a brick wall, okay? And now what happens is the reflected wave gets inverted, gets flipped. And so with the transmitted, I never get an inversion, crest in, crest out. But here I send a crest in and I get a trough out. That represents a phase shift of 1/2 wavelength, 1/2 wavelength. And so here I get no phase shift, here I get a phase shift of 1/2 wavelength. And this is what it looks like. It comes in on the fast and poof, it flips upside down. Poof. Now, why do I bring that up? That's from 105. It's from 1,000,000 years ago. Okay. Well, it turns out that we have to take that into account when we bounce off of these surfaces, when we reflect there. If I'm going from fast to slow, I'm going to get a phase shift of 1/2 wavelength. If I'm going from slow to slower, Okay, that's a case where N3 is bigger than N2. Okay, and this might be some kind of oil and this might be glass. If this has index of refraction of 1.3 and this has an index of refraction of 1.5, I'm going to get a phase shift here and a phase shift there. And that's the easy case, because in that case, hey, we both had some problems, okay? You had a phase shift, I had a phase shift, let's move on, okay? And so we get the same equations as if there was no phase shift, because both of the rays had the phase shift and it cancels out. But what if this is, say, glass, and this over here is more air? What if I've just got a sheet of glass in between? Well, now I'm going to have a phase shift when I go from the fast to the slow, but I'm not going to have a phase shift when I go from the slow to the fast. If N2 is bigger than N3, then this is going to be slower than this. And now look what happened. I'm going to go back. Watch what happened on this slide. Notice the equations didn't change. It's only in this case where I've got two phase shifts. This was for the maximum where I get a lot of reflected light. Whereas if I only have one phase shift, this is for the minimum where I don't get any reflected light. Okay, where all the reflected light is canceled out. Okay. So in this case, this acts like a free end, and in this case, it acts like a fixed end. Okay. Now, this is a summary slide. You got the same equations, but for different things. If I've got N2 bigger than N3, this is the minimum, and this is the maximum. If I have N3 bigger than N2, this is the maximum, and that's the minimum. Okay, that might be something worth putting in your toolbox. Now, why do we care about that? Well, a lot of optics has to do with making sure that as much light gets through the lens as possible. When you're designing a fancy, expensive binocular, you want as much light to come in through the lens as possible, and you don't want any light to get reflected back, because that's wasted energy. You want it all to come to your eye. And so we have to coat those lenses with, we call them thin films, that are just the right thickness to make sure that none of the light gets reflected back. Okay, and when you buy optics, that's what they are bragging about. You know, we have spent years and years studying the coatings. You know, we have all the optimal coatings on this lens. Okay, so here's an example. We've got light of wavelength 665 nanometers, and it's shining on a soap film nearly perpendicular. The soap film has, it turns out soap has an index of refraction about the same as water, 1.33. What's the minimum thickness of the film if this wavelength is strongly reflected? Strongly reflected. Well, if I'm going, I'm hitting, going from air to water, I'm going to have an inversion there. I'm going to have a phase shift there. That's like hitting a fixed end. But when I go from the soap film, which is like water, to air, I'm not going to have one there. And so that means one reflection is phase shifted, the front surface, the back surface is not. And that means that in order to get a big reflection, I want to, first of all, be using the wavelength in the soap film. And so I take the wavelength in air, I divide by n, and I get 500 nanometers. I know constructive interference, if I've got one phase shift, is I've got to have that extra half in there to take care of the phase shift that happened on one surface, okay? So, this would be the formula. What does PLD stand for? Path length difference. That's the delta S that we were talking about before. Path length difference. Now, the thinnest is going to be when M is equal to 0. And remember, the path length difference is twice the thickness of the film, because it's got to go across and across again. So twice the thickness of the film is going to be equal to this value, and the smallest thickness is when M is equal to 0. And so if I plug that in and solve for T minimum, I get 1/4 of the wavelength in the soap. Okay, and so that's going to be 125 nanometers. 125 nanometers. Check to see if your neighbor followed what happened there. Okay. We often see, if you've got an old car, on a rainy day, we see this, kind of a puddle of oil on top of a puddle of water. And it's got this beautiful, pattern of colors on it. And what that is just this reflection where some wavelengths are reflected with constructive interference and some are canceled out with destructive interference. And you get this pattern here. Now, if the oil film has different thicknesses, then different wavelengths are going to reflect strongly at different places on the oil. And I can show that with a soap film here. The soap film, I'm just making film in a circle here. And so if you don't mind, I'm going to turn off the lights. And I'm going to turn off. Okay. Now, if I put it in the soap. I'm going to wait for that soap to create a film. Oh, here we go. As the soap kind of cools down towards the bottom of the loop, you see that it gets thinner on top and fatter on the bottom. And what I end up doing is making the different thicknesses optimum for reflection for a different color. And so I get this rainbow effect. And so this would be an M equals 0, an M equals 1, an M equal 2, an M equal 3, an M equal 4. This would be where I've got it's too thin to get anything there. Okay, that's so pretty, Greg. Why don't you show us more pretty pictures? I took physics first on the island of Guam. My physics teacher was a marine biologist. He had only ever taken one physics class, Physics 105, but he had taken more physics than anyone at the high school. And so he would teach us for about 5 minutes and then show us pictures of sharks. That's how I learned physics. Yeah. You're not as lucky as I am. Okay. Now, so whether I have a vertical soap film that's thicker at the bottom, or whether I have a pair of thick glass plates with a thin air wedge in between, both are going to produce light and dark fringes because of the variance of the thickness of the film. Now, this is what we saw with the soap film, but in black and white here. And so what we see is that in this case, M is equal to 1. No, the M is equal to 0. Here, M is equal to 1. So I had M plus a half is 1/2. This is 1 plus a half. This is 2 plus a half. 3 plus a half. 4 plus a half. Okay, so M equals 0, M equal 1, M equal 2, M equal 3, M equal 4. Now up here, I have not enough film, not enough thickness to get myself a full wavelength. And so it's just dark. It's just not constructive at all. And so this is less than 1/4 of the wavelength in the film. This is equal to 1/4. This, and you can see there, we've just divided by 2. Okay. Now, this is what we've seen, is that if we have a film of air here, at this interface, I'm going from glass to air, so there's no inversion there. But here I'm going from air to glass, so there would be an inversion there. There would be a phase shift of a half a wavelength here, but not there. Okay, so one is phase shifted, the other is not. So for constructive interference, we've got that same formula, but it's an air film. Now, the reason I bring that up is that it's reflected on one side in places, but not in other places. But energy has to be conserved. And so if it's not reflected, then it has to be transmitted. And so what I get, if I look on the other side, is that in places where I get a lot of reflection, I get no transmission. But places where I don't get any reflection, I get strong transmission. Energy has to be conserved. Okay. Now, again, what you want to do with your fancy optics is put a coating that's going to minimize the reflection so that you get as much of that light coming through your lens as possible. And so if this lens, say, is made of glass and you've got some coating there, we can't do this for all the wavelengths. Okay, and so they tend to pick a wavelength in the middle of the rainbow, green, and usually that coating is going to be a smaller index of refraction than glass, and so that means I'm going to have an inversion at this side and an inversion on that side. Okay, and so if I want it to be transmitted, I don't want it to be reflected. Now, this formula that used to give us a big reflection is now going to give us no reflection. Why? Because now we have a phase shift at both surfaces. We're going to that other, we flipped the formulas. And so now this is going to give us no reflection, destructive interference. Okay. Questions on that before I go on? Okay, what's this good for, Greg? Well, one thing we use it for is to prevent counterfeiting with our $100 bills and our $50 bill. What we have is ink that looks different colors depending on the angle that you look at the ink. If you ever find yourself in possession of a $50 bill, you know, look straight on and then look to the side and you'll get different colors. And what you have is a ink that has these flakes in it. And those flakes have thin films. And in those films, this is just a single flake right here. And what you have is a chromium layer that is an okay mirror, and then you've got this thin film of a substance that has an N value that's less than the chromium, and then you've got a good mirror of aluminum, and then another film, and then the chromium. And depending on the angle that the light comes in, that's going to determine the path length difference. And so different wavelengths are going to be reflected strongly at different angles. Oh, someone's got a $50 bill. Okay, ladies, he's the one that's going to have the money to take you out to dinner. Okay. Okay. I just put my wife on a plane this morning with a $100 bill, so I don't have one to show you. She's got it. Okay, so if you view it straight on, it should be a reddish yellow, and if it's at an oblique angle, it turns green. Okay, now a photocopier only scans the currency at one angle, and so you can't just copy your $100 bill. I've tried. When you're creating a lens, say for a telescope, and you want that lens to be perfect shape, you can use what's called Newton's rings. And that is that if you get this shape just perfect, then I can use this the path length difference, 2t, to determine how big t is. And so what you have is m equals 0, m equal 1, m equal 2, m equal 3. And if you keep polishing until these are perfectly concentric circles, then you're going to have the right shape. Okay, that's not going to be on the exam. Okay. We still have 7 minutes. Let's talk about polarization. You remember that light is just an electromagnetic wave. And it turns out that we say the wave is polarized in the direction of the E field for the radiation. And so in this case here, you've got the E field going in the y-axis and the B field going in the z-axis. I would say that the polarization of this wave is along the y-axis. Okay, that's just the definition of polarization. Do you know who that is? I love Lucy. Lucy. You know, what I didn't realize is that she's the one that gave us Star Trek. She's the one that gave the money to make Star Trek happen. Bless you, Lucy. Okay. Now, how do we polarize light? In general, light that's just coming from some random source is going to be unpolarized. The E field is just going to be randomly oriented relative to the direction of propagation. Now, a polarizer will align the electric field. It will only let the light through the polarizer that has its electric field lined up the right way. And it blocks everything else. Okay, now an example of that I've got right here. This is a polarizing sheet right here. And you see that that light there is unpolarized. And when I put this up here, it gets dimmer because now it's all polarized in one direction. And that's going to cut out, just law of averages, half of the light. if all of the light was randomly oriented, then just saying only this light gets through is going to take out half of the light. Now, if I take another polarizing sheet, if I put it with the polarization direction the same, light gets through. But as I turn that, the light doesn't get through. So now they're both blocking the light that's going this way, and so it gets through if it's going this way. But now the bottom one's blocking light this way, and the top one's blocking light that way. We got it all. We got it all. Okay. So you're going to need for your homework that's due next Tuesday to at least understand the first case here. So let's go through that, and we'll cover the other cases on Tuesday. So a polarizer aligns the electric field axis with the polarizer axis. That would be this axis here. And selecting only the component of the light with a Z field parallel to that axis. The other component gets absorbed, okay? Now, if I send something that's just, say at 45 degrees, if I send just general light that's unpolarized through that, half the light is absorbed, okay? And half gets through. And now, if I send another polarizer in front of it, what's going to happen now? So let's talk about that. I'm only going to get the part out that's lined up with this second polarizer. Well, how much is that? Okay. I've got two equations, and only two equations. And these are easy. If you're starting with unpolarized light and going through the first polarizer, it doesn't matter what the orientation is of the polarizing axis is. You get half of the light through, half. And you can divide by 2 pretty easy, no problem. But if you take light that's already polarized and send it through a second polarizer, you're going to take that light that you started with and multiply it by the cosine squared of the angle between the two polarization axes, okay? So here's an eye clicker question. I have unpolarized light that goes through this first polarizer and then through another polarizer that is 30 degrees counterclockwise from the y-axis, and this one polarizes it due to the y-axis. What angle should we use for the cosine squared rule? Is it going to be 30? Is it going to be 60, 90, 100? Okay. You were wondering when we were going to do his clicker. Okay. You can click. Okay. If ever there was a time that we all got it right, this would be it. Last call. Whoa, okay, the answer is A, 30 degrees. Okay. Now, so we started with a intensity of 58 watts per meter squared. Half of that is going to get through, so 29. Okay, and then we take the cosine squared of 30 degrees, multiply that by the 29, and we get the amount that gets through the second one. Okay, we always measure that angle from the direction of the last filter. Okay, so if that's the first filter axis, the second filter would be that one. That's the angle that goes in the cosine squared rule. And if you put the third axis like that, then you would use that angle for the cosine squared rule. Okay, so, one last clicker question. Everyone choose C. That's the right answer. We've run out of time. Choose C. Okay, there's one more person. Come on. There were 140 people left. There you are. I knew you could do it. Really? I gave you an opportunity to go to Disney World and 3 people said, no, we don't want to go. Okay, you have a great weekend, people. Go somewhere else.
Yeah, let's do it. Let's go.